today we will talk about external memory algorithms. What's this external memory algorithms, and why you may want to think about external memory algorithms? Let's see. Usually, when we discuss algorithms, we work in what's called a RAM model, right? We discussed it on the first lecture of the first semester. So usually, when you build some algorithm, you think you're working in a RAM model. RAM model is a very simple model. In RAM model, you think that all your data is stored in some RAM, basically white RAM model. A RAM is basically just a big array. So you have a big array of data. And you can get any piece of this data in constant time. So you can like make array indexation in this language. So you have address in your memory, and you can get this data from this address in constant time. Yep. And like we discussed in the first lecture, this model is quite suitable for standard computers. So if you're working for a standard computer program, usually RAM model is what you need, because in usual computer, in like standard program, you work with random access memory, and access in random access memory is basically in constant time. Not exactly, but it's very close. But sometimes you need some another type, some another model. For example, if you have a lot of data and you cannot store all this data in your RAM, so all your data is stored in some external drive, like for example in hard disk. So you have some hard disk. Let's see. And all your data is stored on this hard drive. Hard drive is quite different from RAM, because in hard disk drive you cannot access any data fast. This happens just because of the physical structure of the hard disk. How the hard disk is working? It's working like this. Basically, you have a disk. And you have some working heads. So you have some. So this is the head of the hard drive. And your data is spread across the surface of this disk. And you only can access the data at this point. So this is the only point you can access the data. So this disk is spinning. So it's spinning very fast. Usually, what is the speed of the hard disk? Let's say about 100 rotations per second. About 100 rotations per second. So it's spinning quite fast. And this speed can give you access to all the data. So at some point, any data can be read by your head of your hard drive. Let's see. So if you want to access some data of your hard disk, what's happening? So imagine your data is somewhere here, and you want to access this data here. So what you need to do is to wait until this point move to your head. So this point is moving here, and at some point you will be able to read this data. What time delay is between you want this data and you cannot read this data? The time delay is the time that this point moves to this point. So it's about one rotation of the disk. One rotation of the disk is about 10 milliseconds, right? So it's about 10 milliseconds. So it's just delay between you ask the disk to read some data and you actually can read this data, just because of the physical structure of this disk, right? 10 milliseconds is, you may think that it's pretty small, but actually it's pretty big time, because your computer can do much more operations per second, right? Your computer can do like billion operations per second, and here you can just like to 100 operations per second. So the difference is pretty big. Let's say if you want to access like byte by byte, like you want just to access random bytes of your hard disk, then the speed of reading this data, so if you just read byte by byte, then the speed will be about 100 bytes per second, right? 100 bytes per second is pretty small, right? In contrast, if you just what you can do, you're not reading data from disk 100 bytes per second, right? You can read that data from disk much faster. Why can you do read from data from disk much faster? Because you are not reading only single bytes. No? Usually you want to read a lot of bytes from disk. If you have a file on your hard disk, then if you want to read the whole file, usually bytes of the file are pretty close on the surface of this disk. So if you want to read this block of data, then you wait until this block reaches this point, and then read the whole block instead of one byte. Yeah, you just read the whole block of this data. And the speed of reading this data is pretty big, actually, compared to this speed. The usual speed of reading data from hard disk, let's say usually it's about 100 megabytes per second. So if you read just random bytes, the speed of this random access will be 100 bytes per second. If you read consecutive block of bytes, then the speed of the consecutive read will be about 100 megabytes per second. So difference between these two is about 1 million. So the difference of time complexity is 1 million. That's quite big quite big difference. So usually we kind of ignore all the constants, right? But it's pretty hard to ignore constant of 1 million, because if in real program you want to read some data from your disk, and you can read it in random way or in consequent way. Yeah, consequent, is it even word? Okay, so the difference of running time of these two programs will be 1 million times. That's a big difference. So this rare model is just not working when your data is on the hard disk. Yeah, we want some different model which kind of uses this fact that reading bytes in sequence is faster than just reading random bytes. Cool. Yeah, so we will move to another model. So we will use another model which kind of simplifies this fact. Model called external memory model. Sequential, yeah, is the word. Oh, cool. How this model is working? Let's say what we want to do. So if you just try to optimize your time of your program, thinking about this structure of your hard disk and all these spinning disks and stuff, it's just too complicated. So when we build some computational model, we want to simplify the reality, right? So you have a real computer, and it is too complicated. There are a lot of different stuff going inside this machine, right? So we want to build some simplified model, but this simplified model should be kind of suitable for this real machine. So how we'll simplify this model? Right, let's see. Let's think. Let's read data in blocks. So if this block have size, let's say b, and we want to read this block, the whole block, then how much time do we need to read this whole block? Let's see, the time of reading this block, let's see, will be sum of two values. First, we need to wait until this block reaches this point, let's see, this seek. And then we just read the whole block. time of reading the whole block is just size of this block divided by speed of reading. That's the total time you need to read this whole block. Now let's think, what is the optimal size of this block? No, the optimal size is basically when these two values are about the same. Yeah? So if this block is small, then this summand is smaller than this summand. So this part will be just much smaller than this part. It means that most of time of your algorithm you just make 6. Let's say if you spend 10 milliseconds to wait until you get your data, then you actually can spend another 10 milliseconds to read this data. Yeah, it's just too stupid to read less data than you actually spent to seek your data. Yeah, so this fraction must be about time of this 6. So this size of this block should be about, let's move it here, so it's the seek multiplied by speed. Well, let's say that time of seek is about 10 milliseconds and speed is about 100 megabytes per second. So if we multiply this by this, we will have something like 1 megabyte, right? So it's kind of optimal to read information in blocks of 1 megabytes. It's not efficient to read data in smaller blocks because we will just spend a lot of time just on these 6 and not on these reads. And it's kind of not important if B is bigger than a megabyte. It means that you spend a lot of time here and smaller time here. But instead of this, you can just make 2 6. This will not affect the asymptotics, right? So if these two sums big, then it's basically, if you think about asymptotical time of your algorithm, it's optimal to make these two parts equal. In practice, actually, you should read in bigger blocks, because if you have blocks of size 1 megabyte, it means that you will spend half of time doing this 6, just doing nothing basically. So in practice, it's better to have larger blocks like 10 megabytes. So if size of block is 10 megabytes, then you spend like 10% of your time just doing nothing, waiting for your data, and use 90% of your time to actually reading some data. So usually it's better to have, it's about 10 megabytes, but it doesn't matter for asymptotics. Yeah. Again, if you understand anything, just say something in the chat, okay? Don't make me nervous. Cool. So, how the external memory is working? We will fix the size of the block. We will say that we only read data in blocks of size B. We will just always read the data in blocks of size B. So the model looks like this. You have your CPU, yeah, this is your processor, and you have some local RAM. So you have some local memory you can access in a fast way. Yeah? So CPU, inside of this you actually have a RAM model, something like that. And you have your hard disk. And you transfer the data from here to here and back in blocks of size B. So you can write data in blocks of size B or read data in blocks of size B. So every interaction between your local memory and hard disk is by reading or writing the block of size B. Nice. Now, the size of your local memory is M. It is another parameter of your model. So, external memory model have two parameters. These parameters M and B are parameters of your model. So, when we will think about some asymptotics of some algorithm, these asymptotics will have some formula, and this formula will contain these two variables. So these variables define the structure of your external memory model, right? So time complexity will depend on the size of the block and size of the memory. Like if you have large amount of memory, the algorithm will work faster. If the size of the block is big, then the algorithm will work faster, and so on. Yeah? Now, how do we measure time in external memory model? Very simple way. We will measure time in number of operations of reading or like input-output operations. So time complexity will be equal to the number of these readings or writings. Reading or writings. Yeah. So we will only measure the number of times we need to write or read the block of data. What's happening inside this model? So inside this model, you actually have some fast memory, so you can access this data very fast. So what we'll do is just ignore everything which is happening inside this RAM memory. So all operations inside this RAM are free. You can do anything here in 0 time. That's a big simplification. In your real program, you actually need to take care of some fast operations inside your memory. But in this model, we'll just ignore this completely. We'll only optimize the number of these input-output operations. We just talked about this. So that's not something you... usually in competitive programming, you don't need to care about this. Sometimes actually you need to care about this when you think. You can actually apply this model not only for data stored on the computer or on the hard disk. You can actually apply the same model when your data is stored in RAM. So instead of having RAM and hard disk here, you can have RAM here and your cache of your processor here. So actually when you have a local cache, accessing your local cache of your processor is much faster than accessing RAM. So sometimes you need to optimize your program to work good in your to utilize your cache in an efficient way. It's basically the same model. Right, different in other situations. For example, when your data is nowadays you usually don't use hard disk, you use like solid state drives, right? For solid state drives, basically the same model is working, but for different reasons. In solid state drive, you don't have this rotating disk, but still the delay between you ask for data and you receive your data is pretty big. So when you want to read some data from your SSD, what's going on? Your processor asks your let's say, I'm not exactly sure how it's going on. So a lot of things happening inside your computer between your processor and your solid state drive, right? So it's asking something, it's going to some buses, I don't know how it's working, no idea. So it's go to the SATA cable and asks the solid state, your SSD. Your SSD is doing something inside, not exactly sure what's going on, but this whole process is pretty long, so it is a big delay between you ask the data and you receive your data. So this time of sitting is not the same as for the hard disk, but still you have some delay between you ask the data and you receive the data. The same thing is happening, for example, if you have data stored on some, let's say, of some remote server. So you have some remote server here, and your data is here. This is your local computer, and this is remote server. And what's going on? So when you need to read the data, you make like a request to the remote server. It's going through your network, then go back, and you have this delay between you ask the data and you actually receive the data. So if you ask data byte by byte, it takes a long time. So you don't want to ask data byte by byte. You want to ask a big block of data. So you ask the data through the network, and you receive the whole block of data instead of just single byte. Yeah, like this. So yeah. So in competitive programming, you might have something like when you have array of data, and when you have a big array of data in RAM, and you read this data like by rows, it's pretty fast because this data is sequential. But if you read data by columns, it will be much slower just because you have a lot of cache misses. And that's usually the same kind of memory model. Now, that's all. That's all about model. That's all. So now what we'll do, we will try to make some efficient algorithms designed specifically for this external memory model. Let's start with something simple. Let's find the sum of elements. So we'll have array A. So this array is stored in your hard disk. And you want to find sum of all elements of this array. Very simple algorithm. Yeah. No, how do you solve this problem in RAM model? Quite simple. You just iterate through all elements of your array and ask them one by one. Yes. So you ask all the elements of your array and just calculate the sum of all these elements. In external memory model, it's actually the same, but instead of reading elements one by one, you read them block by block. Yeah? So you split your array into blocks and read these blocks one by one. So you have these blocks. And you just read them one by one. So you read the first block, calculate the sum of the first block, then read the second block, calculate the sum of the second block, and so on, until you reach the end of the array. So what will be the time complexity? Say something there. Okay, that was a question. Yeah. So if you just read this data block by block, what will be the total time of your algorithm? Yeah, big O of n is not good enough because we are reading data by blocks and we calculate the number of these readings. So we need to calculate not number of elements we read, but the number of blocks we read. So time complexity will be not n, but n over b, like this. That's actually important because n and n divided by b are different in like a million times. So what you want to do is to make algorithms have something like this in time complexity. So your time complexity is divided by b. It's important because the size of block is pretty big. So you want your time complexity to be divided by this size of block. It's important. Now, that's important thing missing in this time complexity. The important thing is this ceiling. Why it is important? Because the time complexity of these algorithms is actually never less than 1, right? So if the size of your array is less than size of block, then you still need one reading to read this whole block. If you just miss this ceiling, what happens? So if you have a lot of small arrays, so if you have n arrays of size 1, yeah. If you have n arrays of size 1, and you won't read them one by one, if you just omit this ceiling, that what was going on? So the time complexity of each read will be 1 over n. Then you will 1 over b. Then you will multiply this time complexity of single read by the number of blocks, and you will have n over b. That's not true. If you read a lot of small arrays, time complexity will be n, not n over b, right? Just because for each of these small arrays, you need to read at least one block from your external memory. And so this ceiling is actually important. Instead of saying, you may do it like this. That's actually the same. Again, this thing is important only for small size of the array, actually. That's not very accurate because big O is actually take care about big size of array, but yeah. And this is important only for small arrays. But let's just keep it like this, just to make it clear. Good. So this is how you read the data from the array from the hard disk. It's quite simple. It's called scan. It's called scan of n is actually let's say n over b like this. But when we're reading n elements, yes, we're reading n elements. Yes, we're reading all n elements. But we read this element not one by one, but in blocks. And in this time complexity, we calculate number of blocks we read. So we need to read these blocks one by one, and the number of blocks will be n over b. Right? Yeah. Again, in this model, we're measuring only the number of these input-output operations. And every input-output operation giving you the block of size b. Let's move next. The next most important algorithm is, of course, sorting. So it's very important to be able to sort the data even if this data is in some external storage. Let's see, sorting. So how to sort the data in the external memory? No, right. So we learned in the previous, in the first semester, we learned a lot of different sorting algorithms. So let's pick some sorting algorithm which actually can take advantage of this technique. So we need to take some sorting algorithm which kind of reads the data in sequential order. Yeah? For example, if you have heap sort, so if you try to sort your array using binary heap, then your binary heap is actually trying to access random elements of your array. Okay? So if you have binary heap, how binary heap is stored in your memory? So you have this. So this array. So each element have some children. So you have this. These two elements are left and right child of your element. So for element I, you have elements like 2i plus 1 and 2i plus 2. So when you want to apply some operations to your binary heap, you need to jump across your array just to access your left child or your right child. And that's too slow, because to jump from here to here, you need to read another block of data. So each time you jump, you need to make another access. Okay? And heap sort, for example, is not suitable. Yeah. Yeah. For example, merge sort. Merge sort will be much better. In merge sort algorithm, we actually read data from left to right, one by one. That's exactly how we do it here. So we will be able to split this reading into blocks and read blocks block by block. Let's see merge sort. So the core operation of merge sort is actually merging two arrays. So let's say we have two arrays. Let's draw them much bigger. Let's have array A and B of size n, and we want to merge them into array C. So how do you merge two sorted arrays into one sorted array? So you have this, both arrays are sorted, and you want to merge these two sorted arrays into single sorted array. How you do it? You look on the first element of each array. So you look on this first element, see what element is smaller, and just remove this element from here and move it here. Then look on the next first elements. See which element is small. So this is small, so you move it here, and so on. So you take this, now you take this, and so on. So each time you look on these two elements of your arrays, see which element is smaller, and move this smaller element to array C. So how to make it in external memory? Actually, exactly like this. We'll do it exactly like this. Here, you need to read arrays A and B from left to right. So we will read them block by block. Each time we need some, so this is the current element of array A. It belongs to some block. This is current element of array B. It belongs to some block. So we will maintain these two blocks in our local memory, so we can access these elements fast. Now, each time we look on these two elements, pick the smallest one and put it here. To put it here, we also need to write elements to array C block by block. So we will maintain some block of array C in the local memory. So each time we will look on these two elements, pick the smallest element, and put this smaller element here. So we remove it from here and move it here. That's all. When we finish the block, we will read the next block. So we will forget about this block, move to the next block, read the next block from your hard disk, and then do it again. So again, you look on these two elements, see which element is smaller, put this smaller element here, and so on. When you finish writing this block, you write the whole block to your hard disk and move to the next block. So you write this block to your hard disk and move to the next block. So now we are reading from these two blocks and write into this block. So these three blocks are in your local memory. When you finish the block, you just read the next block. When you finish this block, you read the next block. When you finish this block, you write this block on your hard disk and move to the next block. Clear enough? Again, the time complexity of this algorithm will again be N over B. So in N over B time, we will be able to make this merge of two arrays. Right? So what will be the total time complexity? The total time complexity of the whole algorithm. So if we can merge two arrays into single array in this time, what will be the total time of the whole sorting algorithm? But it is with sale again. Yeah. I just omit this sailing in the future. Yeah. You need to think about this when you're working with small arrays. But I will just ignore this just for simplicity. Again, what is the time complexity of the whole sorting algorithm? Again, when you do a merge sort, how do you apply merge sort? You split your array into two halves, then apply merge sort to both halves, and then make merge of this. Actually, in this case, when the size of these blocks is less than, if size of this array is less than one block, you can just read this block and sort them inside your memory and then put back. So you can stop your recursion when you reach the size of the block. Not exactly, but quite close. So this is time of single merging. And the depth of your recursion, again, what's happening in your merge sort? You have this whole array, you split it into two halves, apply recursively the same, split it, apply recursively the same, and so on. And this is happening until you reach the size of the block. If you have the array of size of your block, you just can read this whole block, sort it inside, and then put back. Yeah. Right. So this depth recursion will be log n over b. And on each level, we do a merge into two arrays. Merging of two arrays can be done in this time. So the sum of all this merging will be again n over b. So the total time complexity will be actually n over b log n over b, like this. That's all. So if you just take the standard merge sort algorithm, apply it to external memory model, then you will get this time complexity. Nice. Can we improve this? Actually, we can. How can we improve this? Let's see. We ignore very important fact. Let's see. In this algorithm, how much memory actually we need? When we apply this algorithm, we need only 3 blocks of memory. Right? So in this local memory, we use only 3 blocks. So we use this block, and this block. So to apply this algorithm, you actually only need 3 blocks of your local memory. But we may have a lot of local memory. So the size of your local memory is not used in this algorithm. That's not good. Let's try to optimize our algorithm to use our local memory much more efficient. How to do it? No, let's see. Let's try to merge not two arrays in one take, but a big number of arrays. So instead of just merging 2 arrays into one, we will merge just a big number of arrays. We have a lot of arrays. And in single operation, we will merge all these sorted arrays into one sorted array. M over 3. You cannot take. You cannot change the parameter b. You can change the parameter b. The parameter b is just the parameter of your model. You cannot choose size of the block. Again, this block comes from your physical model. Like in your physical model, there is some efficient size of the block, so you can read data. And this is just size of your memory. These 2 parameters may be different. Yeah? So you cannot just say that your size of the block will be m over 3. It's not working this way. Yeah. What I was talking about. So let's try to merge not two arrays in one time, but big number of arrays. So let's see. If we merge these arrays into one, how many blocks do we need? We need to store at only 1 block from each array. Right? So at every moment, we only need 1 block from each array in our local memory. Here. So each time we're reading these elements and write to this element. So we need these blocks in our local memory. So if the size of memory is m, then we can merge not 2 arrays, but about m over b arrays. Yeah. No, it's plus minus 1. I will ignore all the constants, right? So if you try to merge this number of arrays, you will use all your memory efficiently, and it will actually improve your time complexity. Because the now this time complexity, the depth of your recursion will be much smaller. Yeah. Again, what's going on? So in standard merge sort algorithm, you have this array. And each time you split it into 2 parts. But now we can split it not in 2 parts, but in m over b parts. So let's say we split it in 5 parts. Then again, we split each of these into 5 parts and so on. So the depth of this recursion will be much smaller. It will be log of n over b base m over b. And time complexity of this single merge will be the same. So on each level we spend on n over b times, and the depth of recursion will be this. So total time complexity will be n over b log n over b base m over b. Nice, right? So this is time complexity of the sorting algorithm in external memory model. And we can actually prove that this is optimal time complexity. So if you can only compare two elements, then the minimal number of input-output frame operations you need to sort this array is actually this time. So we cannot do it quickly. We can also make back case. Yeah. You can improve it slightly. Just you can split your arrays until you reach the size m. So if size of arrays is m, then you can read you can just read the whole block, sort it inside your memory, and then put back. So if you do it like this, you will have let's move here, log n over b, n over m base m over b. But it's actually the same as here. Yeah. So it's n over m is just n over b divided by m over b, right? So this log is actually the same log minus 1. Yeah. In practice, you can optimize it by just you can stop your recursion when the size of block is m. Then the size of block is m, you just read the whole block in your memory and sort it inside your memory. But it will not affect the asymptotics. Asymptotics will be the same because these two logarithms are the same. That just it just looks better because you in each position you have this over b. If you have n over m here, it just doesn't look that good. Okay? But asymptotics is the same. Yes, you can stop your recursion when the size of block is m. It's also that's also working. Nice. That's all. Do we have enough time? Yeah. Let me show you just how to prove that this time complexity is optimal. This is actually optimal time complexity for the sorting algorithm in external memory model. Let's prove this just very fast. Okay, I'll present just a sketch of the proof, right? I want to prove that this is the optimal time of the sorting in external memory model. Yeah. I will make only sketch. You can put all details as an exercise. It's not that hard. Okay. So let's remember how do we prove that the time complexity, the optimal time complexity of the sorting algorithm in the RAM model is n log n. In RAM model we have something like, so we have this tree of comparisons. So each time we compare two elements, yeah, we get one bit of information. Yeah, I'll just remove this. I don't need to draw this tree. So every time you compare two elements, you have one bit of information, right? And to sort the array, you need to have logarithm of n information, n factorial information. So you need this number of information to sort your array. Logarithm of n factorial is about n log n. I just omit all the constants for simplicity, okay? So logarithm of n factorial is about n log n, and in one comparison, or comparing two elements, we get one bit of information. So we need to compare two elements at least n log n times. So this is why you cannot sort the elements in the RAM model in faster than n log n time. Now we'll try to do the same in external memory model. In external memory model, again, what we need is, first, let's sort all the blocks one by one. Let's treat all the blocks, and now all the blocks are sorted. Just to make it more simple. Now to sort the whole array after sorting all the blocks, we need logarithm. Let me see. So it's logarithm of n factorial over b factorial times n over b, like this, right? Yeah, looks fine. So it's about n log n over b. So we need this amount of information to sort the whole array if each block is already sorted. Yeah. So, each block is sorted, so I divide this by these factorials. So I don't need information inside each block. So now let's think what is the amount of information we can get in one read. So when we read one block of data, how much new information do we actually get? Let's see. So we have, so this is our local memory M, and we read one new block B. Yeah. So we just read this new block. What we can do, we can compare all the elements of this block with all elements inside our memory. So we make comparison between all these elements and all these elements. Now, what's the total number of different results we can get? No, actually, a result we can get is, since we have linear ordering of all elements, right? So we have all these m elements. If we sort them, then these b elements are in some positions in this array. So these are your new elements. Yeah? So if you compare these elements with all elements here, you will find the positions of these elements in the sorted order, right? That's the whole of all information you get. Yeah? By comparing these elements to these elements, you will find the positions of this element in the sorted order. How many positions can these b elements have inside these m elements? No, the total number of positions is just number of so how it's called in English? I forgot about this. I'm not sure, but it's binomial coefficient from m to b. So it's number of different ways to put these b elements in the sorted order of all these m elements. So amount of information we get is actually log of this. This is actually m factorial divided by m minus b factorial b factorial, and it's about b log m over b. So this is the amount of memory b choose b, m choose b. Nice. I need to read more lectures about combinatorics. Combinatorics is my weak point. Okay. Now, so this is the amount of memory or amount of information you get when you read new block block from your disk. So when you read block from your disk, you compare all elements with all these elements, and this is the amount of information you get. And now, we need to get this number of information, and each read gives us this number of information. So just to calculate the number of reads, we just divide this by this. So we have n log n over b divided by b log m over b, and that's exactly what we need. That's all. So actually, if you just make merge sort algorithm when merging m over b blocks each time, then you have the theoretically optimal result. So it's asymptotically the best possible sorting in external memory. Cool. PDF. I don't have any PDFs. Okay, we don't have much time. Okay, let's talk about some different stuff. Let's talk about data structures. Same as the algorithms in external memory, you can make some data structures. Data structures and algorithms are basically the same things. So let's discuss some primitive data structures we discussed in the previous semester. For example, stacks. So how to make external memory stack? So this is stack. You just put some elements here. So you have these are some elements. So you put elements here and pop elements from here. So in external memory model, again, your whole stack is too big to have it in your local memory. So these elements are actually stored in your external memory. And you want some efficient algorithm to work with this stack. What you can do? Let's see. If you only push elements to the stack, never pop elements from the stack, then all you need is to have the last block of your stack. Right? So you have this block in your local memory, and all these elements are on your external drive, right? And when you push new element to the stack, you put it in your local block. When this block is full, you write the whole block to your external drive and then move to the next block. Similarly, when you pop the element from the stack, you just take the last element from your local block. If your local block is empty, you move to the previous block. So again, it's almost the same as we did when we have scan. So we only maintain the last block of our stack. So all these blocks are on the external drive, and this block is up in our local memory. So we can read and write these blocks fast. When this block is full, we move to the next block. When this block is empty, we move to the previous block. That's almost correct, not exactly. Can you see what is the problem here? So if we maintain in our local memory only the last block of our stack, what can we do wrong? Huh? No? Again, I want only the last block. We can do it the last block of size. Yeah, we can do the last block of size M. It's also working. Yeah. Since we have M memory, we can use only we can have the last M elements in our stack. Stack overflow. Yes, stack overflow solves problem, but we will think that the amount of external memory is infinite, just for simplicity. Okay. Yeah, the problem is when we're on the boundary. Yeah. So when we pop this element here, we need to move to the previous block. Yeah. Now, when we call pop operation, we need to move to the previous block. So we move here and take this element. And now when we push it back, then this block is full, so we move back to this block and so on. So every operation, so we push, then pop, then push, then pop. So when we are on the boundaries of two blocks, each operation actually forces us to make one read or write operation. That's too bad. So how can we fix it? We did the same trick when we have when we talk about vectors in the previous semester. We will just store not one block but two blocks. Quite simple. So when we are on the boundaries of two blocks, we will just store both blocks in our local memory. So now we move here, we write data here, and we don't forget this block. We just put both these blocks in our local memory. When this block will be full, we forget about this block and move to the next block. So we will forget about this block only when we move to this point. When we move to this point, if we need to go back here, we need to make at least B operations to move back here. Yeah. So that's how you make external memory stack. What's time complexity? What is time complexity of single operation? So again, time complexity is measured in number of readings or writings blocks of size B. So how many blocks do we actually need to read or write when we make single pop or push operations? Can we shift block by B over 2? We can. Yes. If you can read block from any position, you can actually shift the block of size B by half of the. Yeah. If this separation of blocks is not fixed, yeah. Usually it's easier to think about blocks like of fixed size blocks. So the whole memory is split into blocks, and you can read blocks one by one. Usually it's easier to think like this, but if you can just read the memory from any position, just block of size B from here to here, then yes, you can move your block by half of size block. Yeah. So the time complexity will be actually fractional. Yeah. Time complexity of single operation will be 1 over B. And it's important that this time complexity is less than 1. If you just say that time complexity is constant, that's not good. Because if you say, for example, if time is go of 1, that's not good enough. Not good enough. Because it means that for every operation, you actually need to read or write some data. And every reading or writing operation costs you 10 milliseconds. Yeah? So you don't want to spend reading or writing operation for every request. Let's just write big O here. This time complexity is better. This time complexity means that for each million operations, you have one reading or writing operation in your external memory. So you spend 10 milliseconds not for every operation, but every million operations. That's much better. Million times better. Nice. No, you can also make Q in the same way. Is it obvious? Yeah. So when you want to make Q in external memory, you do just the same thing, but you just put the first and last block of your Q in your local memory, and you just read data from here and write data to here. Okay, I think it's you can do it by yourself. So stacks and queues and all the linear data structures are pretty simple. Let's talk about trees. What about binary search trees? No, just saying that if you have here, when this block is full, you can split this window not here, but here. Okay. And if you do it like this, you always have this spread between your current position and so when you do the separation, you are in the middle of your block. So you need to have at least B operation here and at least B operations here. Yeah. So that's what I was talking about. So every time you have some gap between your current position and the next time you need to make input-output operation. That's how it's working. Yeah, that's the common techniques for all this stuff. So for some, let's say, no, for most of these amortized time operations. So when for example, we did the same when we discussed vectors. So when you enlarge the size of your vector or when you shrink your vector, you need to have some gap between your current position and the next time you need to change the size of your vector, right? And this similar stuff is going on here. So you need some gap between your current position and the next position when you need to make operation. No, you can have window of size M. It will not affect anything actually. Because when you move to here, you need to read another M memory, M element. So you need to make M over B readings to read this next block. So every M over B operations you spend on M. So it will be the same. Now, let's move to the binary search trees. The optimal binary search tree for external memory model is B tree. B tree is the following phrase structure. B tree have nodes. Each node of the B tree maintain about B elements. So you have each node of your binary search tree will contain not single key but B keys. Let's see about B keys. If you have B keys in your node, then like the whole field of elements will be separated into B+1 segments, right? So these are all possible keys. These are your B keys. Yeah. So the whole set of possible keys will be split into these segments. So you have these, and these. And all the segments will be represented by one child of your node. So each node of the B tree will have not two children like a binary search trees, but B+1 children, about B+1. And so on. So it's not binary search trees but it's still search tree. Yeah? No, you can think about it like a binary search tree, but instead each of these blocks may be inside implemented as a binary search tree. So it's actually a binary search tree, but kind of strange one. Again, how to work with B tree? Pretty simple. When you looking for some element, you take the root node, read it from the external memory. Then you have these B keys. You find the position of your key between these keys. So this is position you're looking for. So you know that your key is between this and this. So you know you need to go into this children node, child node. So you select this child node and go to this child node. And here you do the same. You read some B keys, find your position between these keys, and go to some child of your current node. So it's kind of the same like in binary search trees, but you don't have two choices. You have B+1 choices each time. So what will be time complexity? Time complexity will be, so if you have n elements, here you have one element. So each time the number of elements is divided by n over b, by b, so the time complexity will be log n base b. So that's the time complexity of operations in B tree, in external memory. I think you can prove that it's optimal. Yeah, I think you can prove that this is actually optimal for the binary search trees in external memory model. What's interesting? We just say that this time complexity is bad, but here we have even worse time complexity. Yeah. So we don't want data structure which forces us to make input-out operation for every operation. But here we have even more. We have more than one operation. For each request to the binary search tree, we make more than one request to the external memory. And we just said that even one request costs you 10 milliseconds. So you kind of don't want to spend 10 milliseconds for each request. But here we kind of had to. Why we had to do it? No, basically because of the just nature of the binary search trees. For binary search trees, what is specific of a binary search trees? In binary search trees, you can access any element of the binary search tree. So you can, in binary search tree, you just have operation find. This operation finds you some elements of the binary search tree. So you can call, you can make some specific call which accesses the specific element of your binary search trees. And since you have n elements, you can access any of these n elements of your binary search tree. And to be able to access all elements of your binary search tree, you kind of had to make at least this number of requests to your external memory. That's life. That's hard working. Basically, binary search tree is not very efficient for external search memory. Usually, when you have some external memory algorithm, you don't want to use binary search trees, just because each request to the binary search tree costs you this amount of time, and that's too much. So usually, you kind of want to avoid using binary search trees in external memory algorithms. In comparison, for example, stacks are good. Stacks are good. Heaps are good. You can make fast heap in external memory. I will not talk about fast heaps this time, but you actually can make fast heaps in external memory. That's complicated, but you can. What is different between heaps and binary search trees? The key difference is that in binary search trees you can access any element, and heap you can access only the minimal element. Yeah. So what happens when you have heap? You can insert element, or you can remove the minimal element. So you only access the minimal element of your binary heap. So there is only a small set of elements which can be accessed in the next number of operations. If you have sequence of operations, then you always know that next few operations will access only some small subset of small elements of your heap. So you can maintain all the small elements of your heap in your local memory, and all big elements you can store on your hard disk. So that's the difference. In binary search trees you cannot do it because you can access all elements of the binary search tree. Well, similar with the let's say hash tables have the same problem. You cannot build fast hash table in external memory, just because in hash table you can access any element of the hash table. That's the problem of all maps or sets in external memory. Do we have time to do something else? I'm not sure if we have enough time, actually. Okay, let's solve a few more problems. That's a nice topic. We can make another lecture about this, actually. It's a nice topic. There are a lot of very interesting algorithms about in external memory model, just very specifically designed for external memory model. Let's solve two more problems. Yes, we have enough time to solve two more problems. Just to give you some sense of what's going on when you design some algorithm in external memory model, and what problem you have. That's the last lecture of the semester, so maybe you need to go to the previous lectures of this semester if it's not. That's kind of complicated stuff, yeah. So you need to start with something more simple. Just watch all the previous lectures. In the first semester were much easier. Let's go. Okay, let's solve the following problem. We have some permutation. Let's have something like 3, 1, 5, 2, 4. So it's permutation. Permutation. Yeah. Permutation just means that we have each element exactly once. Just permutate somehow. Huh? What I want to do is to build reverse permutation. So I want to build array R such that R of P of I equals to I. It's called reverse permutation. Now again, if you have RAM model, you have no problems, right? You just make like this. So make 4i from 1 to n R P I equal to I. That's how you make reverse permutation in RAM model. You cannot do it in external memory model. Because in external memory model, you cannot access random element of array R. So in external memory model, you need to be more, how it's called? So you need to do something more interesting. Let's move. So what's the plan? How will we make the reverse permutation? The easiest way to do it is like this. We will make the array of pairs. Again, what does RPI means? It means let me write it like this. So I want to do these operations, right? I want to access the element with index pi to I. I want to make all these operations in sequential order. So what I will do, I will put all these operations into list of operations and then sort this list. Let's watch. What's going on? Again, I want to put the element with index pi, value I. What I will do, I will write all these operations into array as a pairs. So again, let's see, I have this array. Yeah. So what I want to do, I want to put in array R on the third position value 1, on the first position value 2, on the fifth position value 3, on the second position value 4, and on the fourth position value 5. Yeah. So these are pairs pi and I. Again, I just look at this code. In this code, I want to put in position pi value I. So let's write all these operations into list. So I have this list of operations. So I want to apply these operations to my array. And now I will just sort this list and make these operations in a sequential order. So I will sort this list by the index of the array. So I just sort this list by this. So I have 1, 2, sort. 1, 2, 2, 4, 3, 1, 4, 5, 5, 3. And now after this sorting, I have all these operations sorted by the index of the array R. So I can just go in this order and apply all these operations. Nice. So I put the first element to 2, second element to 4, then to 1, then to 5, then to 3. So this is the array R. That's all. That's how you build the inverse permutation in the external memory. So again, in RAM model, when you need to build the inverse permutation, you just make something like this. So in RAM model, you do it like this. Now, in external model, you cannot do it like this, because here you access some random elements of your array. But since the order of this operation doesn't matter, we can perform these operations not from 1 to 1, but in some different order. So I will just just get the list of all these operations, then sort these operations in such a way that I will later be able to make these operations from left to right. So I just write all these operations, sort them by the index of the array R I need in this operation, and then apply these operations one by one. Clear enough? Okay, hope it's clear enough. And total time complexity will be the same as sort. So the slowest part of this algorithm is this sorting. So I can make the inverse permutation in, again, n over b, log n over b, n over b time. And that's quite common thing in external memory model. In external memory, usually what you want to do is to make something, then sort this something, and then apply your algorithm. So all basic algorithms in external memory model actually based on this sorting. No, just because you want to make operations in some sorted order to make it faster. So you do something, then sort this, and then make operations in this order, and it is the fastest way to do it. It's kind of strange that some kind of algorithms looks like linear algorithms now have this log n in the time complexity, but that's how it's working in external memory. Do we have time? Oh, we have enough time. Okay, let's solve one more. Oh, sorry. Yep. Second one. You have two arrays. You have array A and array B. And I want to build array C such that C of I is just, let's say, B of A of I. So I kind of make, how it's called? I want to make just a combination of these two functions, right? So I want to apply function A and they apply function B, something like that. Again, I want to use these elements of array A as indexes in array B. So Ci is element of array B with index AI. How to do it? Well, it's actually pretty much the same as here, but just let's look on this problem from another perspective, just to make you just different views on the same problem. How you can think about this? Let's write down all the pairs. So you have this I, A, I, like this. Let's store it like this. 1, A of 1, 2, A of 2, 3, A of 3, and so on, n, A of n. So let's make this array of pairs, and here let's make another array of pairs. A1, B of 1, 2, B of 2, 3, B of 3, and so on, n of n. Now, how to construct array C? When you want to make some elements, C2, what's going on? You take this element A2, yeah. Now use this element as index in array B, so you go to some position here, and take this element as C2, right? So again, how to find the element C2? You take the second element of array A, find the corresponding element here, and here find the corresponding element of array B. That's all. That's how you find them. So to make it fast, you kind of need to join these two tables. If you're working with databases, that's how you join tables in databases, right? So you have these two tables in database. You need to join this column with this column. Yeah, kind of like. So for each element here, you want to find corresponding element here. And how to do it? Is you just sort both these arrays. So you sort first array of pairs by this column, and this array of pairs by this column. No, it's already sorted, so it doesn't matter. So this array is already sorted, but you need to sort this array by this column. And now, after you sort these two arrays, you just need to assign, you just need to kind of join these two sorted arrays. So for each element of the first array, you need to find the equal element in the second array. And if both arrays are sorted, you can do it like you do merge sort. So you have two pointers here and here. And every time you move this first pointer, you move the second pointer to corresponding position. So you can assign this element to this element. And each time you find the corresponding element in the second array, you find this value of array B. So you kind of make this join using two pointer methods. And for each time you find these equal elements, you know the element of array B corresponding to index equal to this element of array A. So you know what element you should put in array C. That's how it's done. So again, you just sort this, make two pointer method to assign element to the corresponding element here, and find all elements of array C. Again, the slowest part is just to sort this to array of pairs. So the sorting is working in this time complexity. The total time complexity will be again the same as the sorting algorithm. That's all. And now some more complicated algorithms in its own memory actually uses stuff like this. So what you want to do is to split your algorithms into phases, and so in each phase you need to do something like that. So you need to combine some arrays into something new, and then you do these operations something like that. So each time you sort something and then assign this and make the combination of these arrays. And when you just split your problem into separate problems like this, and then the time complexity of each such operation will be the same as sorting. Okay, I think that's enough for today.